Hi everyone. I'm going to start looking at chemical kinetics number 2. Now, if you remember, part 1 was just the basics, right? Remember this? So the rate of a reaction is essentially the rate at which the reactants bump together. Okay, and what we can do in our lab, well, there are 4 things, right? So if you remember that from the last one, and the 2 major ones were concentration and temperature. If you think about it, hey, if I increase the concentration, the particles are closer together, so they bump into each other more often. If I increase the temperature, they move around faster, so they bump into each other more often. Chemistry is all about things bumping into each other, right? Okay. Now, kinetics 2 is all about the concentration part. Okay, so those 2 main variables, things we can change in the lab, concentration and temperature, parts 2 and parts 3 respectively. All right, so kind of talk about there in the key. So we can either in a lab change the concentration of the reactants or the temperature at which the reaction happens. Increasing either or both will always increase the rate of reaction. Okay, so now if you remember the last time I showed you that graph of, the classic, right? I'll show you it again in a moment, and this is true for your lab this week too. So you have time and concentration, say, of reactant, right? And they always look like that, okay? The graphs always look the same, yeah? So they have an exponential decay, concentration of reactants, or an exponential growth over time for formation of products, all right? So when we look at the initial rate, that's when t equals 0. Okay, so we looked at instantaneous rates. We could look at the gradient at any point in time on that slope. The instantaneous rate is the speed at that particular point in time. At time equals 0, we have what's called our initial rate. Okay, so time equals 0, initial rate, or if you like, instantaneous rate at time equals 0. They're kind of synonymous. All right, so let's think about this very simple concept, right? So what happens to the rate of any reaction when the concentration of the reactants is increased? Well, if the concentration of the reactants goes up, collisions per second goes up because they're closer, rate will increase, okay? So we mentioned that already. Rate increases as concentration reactant or reactants goes up. Now there are subtleties in the kind of magnitude of the increase in speed depending on the type of reactant. We'll get to that actually in a couple of pages time. Okay, but if I just across the board, all the reactants increase everything, it's for sure going to go up because there's more collisions per second. Okay, so we can write that down. More collisions per second. Explanation point, right? We're always doing that. Therefore, faster rate. Okay, now this initial rate method, I think if we did this in the lab for real, we'd look at a classic experiment with iodine, and iodine is a classic kind of purpley brown color, and as that's used up as a reactant, we can actually monitor the amount of iodine present with our eye. So all we need is a watch and our eye to do a very nice experiment. I think, I haven't checked fully, but I'll double check later, but I think it may be the iodine experiment also on your pivot, so I'll check that later. Okay, so either way, classic iodine experiment. All right, so overview then. So the initial rate method involves, finding that rate, that curve's kind of tangent line slope, right, at t equals 0. Okay, and why would we choose t equals 0? Because every reaction, doesn't matter how fast or slow it is, everything starts at t equals 0. So compare apples with apples, we always start at t equals 0. That's called the initial rate. Okay, so we can again look at the rate of disappearance of a reactant or appearance of a product. The slope at t equals 0 for one of those. All right. Now what we're going to do, we're going to generate what we call the rate law equation. Okay. Now be careful. Rate expression was last time. That was the relative thing with the stoichiometry from last packet, right? The rate law equation is actually a mathematical equation which allows you to determine the speed of reaction for any condition of concentration of reactants. Okay, so it's a relationship between concentration and speed for a reaction. Okay, so a very powerful piece of mathematics. You can actually predict if I throw these 2 things in there, these 2 reactants at these specific concentrations, how fast will it go? And you can figure that out. All right. So there's our generic graph again. Okay. So you saw that one last time. Now, as you remember, okay, I'll move that so you can see it. The initial rate is the instantaneous rate at time equals 0. So that's here, right? Okay, that's t equals 0, so there, right? Okay, so we can either use a computer or, software to kind of get like half the tangent, if that makes sense. So we're kind of extrapolating backwards and forwards, trying to get the slope. We do rise over run there. Slope for A. So if you remember A from previous packet, that's the true initial rate, if you like, because I'm measuring exactly at time equals 0, making a tangent. Okay, if we can figure that out, fantastic. We'll just do lots of these plots through different concentrations, right? And then we'll be able to, I'll show you, we'll be able to do our initial rates method. However, let's say we can't have the calculator or the computer rather determine that, okay? The computer can't hit it. Heard that somewhere before.
That's impossible, even for a computer.
Oh, yeah. Okay, let's say more realistically, we're going to have data points, right? So remember, each one of these points on the line is a measurement of concentration at that particular time, okay? So we're able to measure some concentration at some time, right? Okay. And if you think about it, we can have the, y2 minus y1 equals mx2 minus x1. We can look at the first two data points here and get a pretty reasonable approximation for the slope at time equals 0 by looking at the first two data points and the slope between them. That's probably what you'll do. Okay. Now, if you think about it, if we set up our experiment to measure data points as rapidly as possible, that will make that distance shorter, which would make the determination of initial rate more accurate. Okay. So when we set up our experiment, we try and make the data points collect quickly, so we get a nice short distance between data points. We can work out a nice slope at pretty close to t equals 0, get a nice initial rate. Okay. So back to it. So we're going to, just to recap, we're going to record raw data, just like I think you did in your last lab, for different conditions of concentration for reactants, right? Okay, and then find for those, maybe we'll do 5 or 6 plots. I'll show you how to set up a table later, but however many plots we do, we'll always find the slope right where it starts, the initial rate. Okay, now we use that initial rates data, and I'll show you a table in a moment, to figure out this rate law equation, right? Okay. Now let's talk about that. So how can we kind of rationalize I'm not just going to give you the equation. We're going to talk about how it's kind of obvious when we look at it, why it's the way it is. Okay. So how would you expect? So if we can kind of answer these questions in our head, we can actually convert those thoughts to math, right? Okay. So how would you expect the initial rate, i.e. the speed at time equals 0, of a chemical process to vary with concentration of reactants? Well, the rate's going to go up as the concentration goes up, right? So we've got a very simple concept to start. Here we go, we write it. The rate is proportional to the reactants. Now, I've got to, put them all together, right? So if I increase them all, I'm for sure going to get a rate increase, okay? Now, that's important because when we go on to kind of individual reactants, some are more important than others, it turns out, right? So would you expect all of the reactions to be equally important? Not necessarily, right? Sometimes they are, sometimes they aren't, okay? But we have to kind of factor that in. And to do that, we do what we call orders of reaction, okay? So for example, if I had A plus B turns into C, it's that classic equation, right? So these are the two reactants, right? So they bump together and stick to make this thing C, right? Okay. So rate is proportional to the concentration of A times the concentration of B. So it's got them both in the equation. But wait a minute. If something's more important, if I make its concentration go up a little bit, I'll have a big change on rate, right? So if I put maybe powers up here, if I put a 1 here as a power, that would be directly proportional, right? If I double this number to the power 1, it stays the same number, rate doubles, right? If I put a 2 up there, hey, double the number, 4 times 2 squared is 4, right, for example, 4 times faster. So whatever the power is up here, it tells you kind of how important that reactant is to the process. And we'll do it generically right now. Later on we'll put numbers in, there'll be 0s, 1s, and 2s. And these are called orders. Okay, so each reactant has an order which determines literally how important it is, right? So 0, 1, or 2 orders of reaction. And they're with respect to each reactant. Okay, so each reactant will have its own unique order, which, very, very important, can only be determined by experimentation. Okay, you can't look at the stoichiometry. Okay, we'll see in more detail why later, but you have to do the initial rates method to figure out these orders of reaction. Okay, so we've still got a proportional there. We'll get rid of that in a second, but that's basically the crux of it, right? So rates proportional to the concentrations of the reactants raised to certain zero or integer powers, 0, 1, or 2 usually. Okay. Now, okay, you can get rid of a proportionality by putting in a constant, and this is what you'll see in the book. So the book one's a little bit more detailed, but it's kind of the same thing. So A moles of A reacts with B moles of B to make C of C and D of D. Remember, it's all about these things bumping together. Okay. The rate equals the rate constant, okay, K for constant, right? That's just what we do. K for constant. So that gets rid of the proportionality. A to its order, B to its order. You'll notice A and B in the front here are not the same as M and N. They may be coincidentally, like 1 and 1 or something, but not necessarily. So again, you've got to get this from experiment, okay? Experiment only. Okay, now, we'll actually come back, as we go through, this will make more sense as we talk, all right? We'll come back and look at this in a moment. But let's just remember what this means, right? So the rate, if I go up here, the rate is change in concentration of a chemical with time, all right? I have to keep moving backwards and forwards. K is a rate constant. It's a constant at a fixed temperature. K does change with temperature, but this is all at 25 degrees C, so K is fixed. It's a constant at a fixed temperature. And that's determined, again, from interrogating data, which I'll show you an example in a minute. It will have unique units based on the powers of the concentrations. Obviously, A and B are the concentrations of the reactants, and M and N are the integer orders of reaction, which kind of tell you how important that reactant is. Orders are always either 0, 1, or 2, for reasons, again, we'll talk about later. All right, so I'll move that up. So there we go. You can read it. Okay. Now, so I'm going to show you a technique. Okay, there's kind of an intuitive way to do it and kind of a mathematical way to do it. I'll show you both. All right, show you both. But on the test, when you do this on the test, even if you do the intuitive way, you've got to show the kind of pseudo math, which I'll also show you. Okay, so you can do like the full kind of simultaneous equation, like you know from math, or you can do like a more kind of inspection type thing. Okay, now if you're smart and you set up your experiment correctly, inspection is probably the way to go. Okay, but you should know the math way, because sometimes in the ACS they don't do the standard method. Okay, I'll show you the standard method in a second. All right, but hey, if you know the math, you don't need to use the shortcut. All right, so the rate law equation obviously relates to the speed relating to the concentrations of the reactants raised to some power. Those powers are called the order with respect to that particular reactant. Okay, then if we add them together, if you actually say you had, like, 1 and 1, it'll be second order overall. You just add the orders to give the overall order of the reaction. Okay, and again, they're always 0, 1, or 2 for the individual reactants, and you can again only get it from experiment. Okay, only get it from experiment. All right, now, so here's a classic, simple one to start, right? So it's kind of interesting because you can kind of sort of see the mathematics kind of behind the curtain a little bit just by looking at the numbers. Okay, now this is how we always set up a study. Okay, now look how we got it set up here. So we've got A and B, which are 2 reactants, right, turn into C. Yeah, okay. What we do, if you like, if you just look at these numbers, so we can put 0.1 and 0.1 moles per liter in a flask, say, and maybe that's looking at the rate of appearance of C or something, right? So we got some rate and we got some conditions of concentration of reactants, right? I like to call that the baseline. Because look what we do. We systematically, in experiment 2, we keep A fixed but double B, right? So hey, so essentially what B is telling you, sorry, what experiment 2 is telling you is what's the importance of B in the whole scheme, right? If we look over here, the rate doesn't actually change, so it's not important at all, right? Okay. Then if we look here, then we keep B at 0.1 just like it was in the baseline, and double A, well, it goes up by a factor of, hey, squared, right? 4 squared is 16, right? So it goes up by a factor of 4. So that's super important or very important. That's not important. Look at the rate. The rate didn't change when we doubled b, so it's not important. That's actually, we'll find out it's going to be 0 order, right? And this one, well, we doubled this and it went up by a factor of 4. 2 squared, right? 4. So that's actually going to be second order, as we'll see. Okay, now that's a lot to digest, all right, and you'll kind of pick up where we're going as we go through. But let's look. So find the rate law expression for this process. Rate law equation. I'm going to put an equation there. Find the rate law equation for this process, which is quantitative. It will have numbers and units. Okay. Part of that is finding the value of k in its units, and then we'll use that equation once we've got it to figure out what the speed is under these conditions of concentration. That's the point of it, right? So the point of making this equation is you can figure out how fast it's going to go when we have these concentrations. Okay, so we kind of mentioned it already. Right off the bat, looking at the table, which reactant has the biggest effect on initial rate or reaction rate overall? It's obviously A, right? Because we double A and it goes up by a factor of 4 compared to baseline, right? Okay. So write that down there. A, biggest change in rate. Oh. It went up by 4. Okay. 4 squared, right? Okay. Here, which reactant had no effect? Well, it was B. It was the same rate when we doubled B. So B, no change in rate. If you like, you're multiplying by 1. Okay, anything raised to the power of 0 is 1. That's where we're going to get the 0 order in a minute. Okay, what's happening on the macroscopic level? Well, only collisions involving A are, oh, leave it up, important. And then we'll see that in the math, okay? So when you change the concentration of A, you see a massive change in speed of reaction. When you change B, you see no change in the speed. So only collisions in, you know, because it's all this, right? So maybe on the microscopic level, and we'll talk about mechanisms later, maybe A has to bump into A before it bumps into B or something. And we don't know, right? Because we can't kind of get down there and see that, but we can kind of interpret that, right? So only collisions among A are important, right? Okay, because it has such an effect on rate. All right, so let's get into the math. Okay, so the plan is pretty much always the same. You do a few of these, and I've got a few exam questions in the back of the book, right? Okay, back of the book, back of the packet. All right, so what you're going to do, you're going to solve for M, N, and K in the rate equation, okay? You can do it through observation, which we'll talk about next, but if you want a non-fail, works every time method, we'll do the math method first to show you. Okay, the math method is actually preferred for experimental data, and we'll talk about why later. But hey, on a test, oftentimes you can do the, you know, well, either, to be honest. Okay, so once we've got M and N, through doing the math or observation, we'll find K through insert and evaluate. Then we've got our equation. We can just then stick numbers in the equation and get an answer for rate at any condition. Okay, so let's look at it. So it's probably a good idea to have the data sheet kind of sitting kind of handy so you can look at these values here, right? Okay, so find the order of each reactant. You got to compare the data sets, okay? So it's always kind of n plus 1. So you have one experiment for each reactant, if you like, changing, and then the baseline where you don't change any, right? So if it was 2 reactants, it's going to be 3 experiments, etc., right? So 3, there'd be 4 experiments, etc. Okay, so math or observation? Math first, okay? So what we're going to do, we're actually going to write out these equations, but put numbers in them, and then divide, and it's like a simultaneous equation in math, right? Now, if you think about it, if we did, we're going to compare 1 and 2 first, right? So we'll compare 1 and 2, and when we're going to divide them out, right, we'll always put 1 on the bottom because it's a smaller number. So we're always going to divide a big number 2, for example, by 1, right? Okay, so we're always going to compare to that baseline, okay? And we're going to write it in the same form as it is here, and then we'll just divide them out and see what happens, right? So make sure I got this right. So I have this sitting on the side. Okay, maybe I'll do, nope. Maybe I'll insert the numbers for number 2 and you can do number 1, right? So number 2, the rate, right, is 4 times 10 to the minus 5 moles per liter per second, all right? The rate for number 2, 4 times 10 to the minus 5 moles per liter per second. And 0.1 and 0.2 for A and B, I'll put those in, right? Equals K, we'll figure out K later. A was 0.1 mole per liter raised to its power, right, times 0.2 for B raised to its power. Okay, fair enough, right? So what I want you to do a similar one for condition 1, experiment 1, okay? So the rate, K, is going to be the same, and then the concentration is raised to the same orders, all right? Let's do that. If we look, the rate didn't change between 1 and 2. It's the same number, and it's 1 and 0.1 and 0.1. So 4 times 10 to the minus 5 moles per liter per second equals K, 0.1 m for molar, right? 0.1 m. Okay. Now, what I'm going to do, I can't find my trusty ruler, so I'll just draw it freehand, right? All we're going to do is just divide these out now. Okay. Divide 2 by 1, and remember, because 2 will contain bigger numbers, right? So it'll be a 2 on top and 1 underneath, essentially, in a moment, right? So what do we get? Equals, let's divide them out. Same divided by same. They're identical, so that's just 1. K divided by K, 1. 0.1 to the m, 0.1 to the m is 1. See how, this is why it's important to set up your initial table correctly, because these all turn into 1s, right? And then we got, hey, 0.2 over 0.1, if you remember a little bit of math, right? So a number divided by a number to the power is the same as the 2 divided to that power. So that's 2 divided by 1 is 2 to the n. There we go. All right. So 1, 1, 1, 0.2, 0.1, 2 to the power n. Okay. So therefore, 1 equals 2 to the n. Therefore, n equals, now, careful, do you remember your powers, right? So if n was 1, 2 to the power 1 is 2, right? So that would not be equal. If it was 2, 2 to the power 2 is 4. Here's your trick, right? What if n is 0, any number raised to the power 0 is 1, isn't it? Okay, so n must be 1. Sorry, n must be 0. Say that again. Any number raised to the power 0 is 1. 100 raised to the power, put it on the calculator right now. 100 raised to the power 0 is 1, right? Anything raised to 0 is 1. So n equals 0. Okay. So if we go back up here, we got that number there, right? So we put that in a moment. In a moment, we'll sub 0 for n, right? Okay. Keep going. Now, we'll be systematic about it, right? So we just compared 2 and 1, right? Now we're going to compare 3 and 1. We're always going to compare to that baseline, yeah, because it makes the math easy, right? Okay. So, compared to the baseline, well, why don't you try it, right? So pause me, try it, see if you can determine the value of m, okay? All right, and I'll go through it. You're back? All right. So 3. Now, this isn't strict scientific notation, is it? It's just 16 times 10 to the minus 5 just tells you it was, 4 squared, right, essentially. Equals K 0.2. We changed A that time. 0.1. Here, same as before. 4 times 10 to the minus 5. I'm being a bit loose with the units here because they're all going to cancel like last time, right? But on the test, make sure you show them. 0.1, 0.1. Okay, divide them out. 16 divided by 4. 4. Equals. K is 1. 0.2 over 0.1 is 2 to the m. And then 1, right? So therefore, 2 to the m equals 4. Hey, 2 squared is 4. M equals 2. All right. That was easy, right? So if I'm kind of like thinking about this on the fly, what I've got so far, I've determined rate equals k. K is yet to be determined, right? A to the 2, B to the 0. Nope, 0. All right. Fair enough. Okay, so that's on the fly, right? That's on the fly. We're not done because we haven't got k yet. Okay, I haven't got k yet. All right. Now, let's talk about the observation method real quick. So, what did you notice? And you can see it right here, yeah? Okay. So actually, let's go back. So just some observation. There's my baseline, 4 times 10 to the minus 5 moles per liter per second. I doubled B, nothing happened to the rate. So that means 0 order, right? Okay. Here, A, I doubled, and I got 4 times faster, so it was squared. Okay. So this only works when we're doubling, all right? If you look at what happened up here, and we can see it kind of in the microcosm here, right? So for easy numbers, okay, like in this example, all we got is the factor of the reactant is multiplied. And if we're clever, we always make that 2. So if you notice in that table, we systematically doubled reaction concentrations, right? So that's always going to be a 2. But there are some tricky questions when that may be a 3 or a 4. So watch that, right? Okay. If you set up your own experiment, we always double, all right? Okay. So the reactant concentration multiplier between trials, right, for that particular reactant, raised to the order, which we saw up here. So there it is there, right? That's what popped out. So that's what happened when we divided the rates, right? Oh, here. Sorry, that's what happened when we divided the concentrations. The concentration multiplier to the order equals the rate factor increase, right? So it went up by a factor of 4. So that's 4. So 2 to the order is 4. Okay. So if you can see that, if you can see the forest for the trees, so to speak, right? Okay, it makes life easy, doesn't it, right? So if A is doubled, well, B remains constant, and the rate goes up by a factor of 4, we have this situation, all right? So that's the rate increase. That's the order, and that's the concentration multiplier, if you like. Okay. So, what's the value of m? Easy, right? 2 to the power 2, 4, therefore m equals 2. Nope. 2 to the power 2 equals 4, m equals 2. Okay, so we'll actually do the a few more examples. We'll do it both ways, all right? But if you got that math trick, fantastic. But don't rely on it. Do not rely on it. If you're in any way, shape, or form a little bit fuzzy on that, and if you ever use experimental data, if you use experimental data, the numbers are never nice and easy like 2, are they, right? So it only really works with kind of manufactured data, okay? So, you know, your default position should really be the math, okay? But if you're in a position where the numbers are easy, you can do the observation method. And I call that there. That's sufficient work for the observation method. Again, you'll get used to it as we go through, but that's the observation method. All right. Hi everyone, minor technical issue there, back again. Now, try and do what we just did, but for the other reactant, okay? So, analyze data sets 1 and 2, determine the order through observation with respect to B, okay? So if we just look at it, what do we got? We're changing B, right? B doubles, so our concentration multiplier is going to be 2, right? We see, if you like, a rate multiplier of 1 because it's the same number, it's just multiplied by 1. So, doubled, 2 raised to the power, the order, equals 1. All right. I actually did this earlier and the camera turned off, so there we go. So, the concentration multiplier was 2, raised to the order equals the rate multiplier, which was 1. There it is. Anything raised to the 0 is 1, n equals 0. Okay, so that's observation method. Now, we saw that one earlier too. We can now just include the orders as actual numbers, right? So 2 and 0. So we'd say second order with respect to A, 0th order with respect to B, second order overall. What does that mean? Well, it means for both of them, 2 plus 0 is 2, right? So you add the orders, that's the overall order. Okay. Now, moving on, so we said it there. The reaction is said to be second order with respect to A, 0 order with respect to B, and second order overall. All right, so mentioned it already. I just go back and, excuse me a second, find my notes here. So I want to make sure I get the right verbiage. So what does this statement mean in terms of how each reactant affects the overall rate of reaction? Recall previous graphs, okay? So have these ready kind of at your side, and I said we'll come back to them. There it is, okay? So particularly I'm interested in, well, either of them really. Let's look at this one. So reactant concentration versus time. So there's a concentration versus time. And you can see for a 0, a first and a second order, we have an increasing exponential kind of function, okay? So, you know, squared, proportional, and then 0, right? And then here we see a rate versus concentration. 0 order, the rate stays the same, right? It's just 1, isn't it, right? Here it's directly proportional. So in the first order we have direct proportionality. Second order we have an exponential kind of shape. Okay, so 0, first and second order, rate versus concentration. All right. Now, what does this statement mean above here in terms of how each reactant affects the overall rate of reaction? The rate of reaction is proportional to A squared. The rate is proportional to A squared. It's got like, it looks like one of those kind of, you know, y equals x squared graphs, but just the kind of the bottom right hand corner, right? So that's your squared dependence right there. Okay. The rate of reaction is unaffected by the concentration of B. So it's got to be B to the 0, right? If we look at that graph again, flat line. So the rate stays constant, right? It doesn't change. Yeah, I mean, the reactant will disappear over time, but it's not affecting it, right? The concentration of A does not affect the rate. Okay, so there it is there. Okay. All right, and should we have a first order? It's directly proportional. All right. Okay. As we said, the reaction is second order overall. We call that one 0 order, and that's second order. Okay. Now, how is the overall rate related to the individual orders of reaction? Mentioned it already. Sum them up, that's your overall order. So the overall order, so the reaction as a whole has an overall order of reaction. is the sum of, I'm writing on this line here, the individual orders. So above 2 plus 0 equals 2. That was with respect to A, that was with respect to B, that's overall. Okay. So if I write that kind of more neatly, A was 2, B was 0, therefore second overall. If I had like two first orders, this isn't what we had just now, let's say it was, that would also, first order and a first order is second order overall, as is a second and a 0. Just sum the orders. All right. Now then, finding K. I've kind of run the math here for you. Okay. Oh. There we go. So, keep going back to here, right? So, we've got to find the numerical value of K in its units, okay? Because we have the orders now, we can literally just take the data from one experiment, and you can choose any of the three. If you want to just do an intellectual exercise, do this for all three experiments, and you'll always get the same answer because K is a constant, right? But you know, typically we'd just choose experiment 1. We'll plug in the numbers, rearrange to find K. So we have rate and concentration for experiment 1. 0.1, 0.1, 4 times 10 to the minus 5 moles per liter per second. We just throw those in and rearrange, right? That's all we're going to do. So, kind of said it here. So we're going to take the equation. Now, if you think about it, I'll put it there. Anything raised to the power 0 is 1. So you can just, if you've got any reactant raised to the power 0, just write it as 1, or just forget about it, because multiplying by 1 is the same thing, yeah? So this is the same rate equation we had before. It's just that b to the 0 is 1, so it's not even affect the math, is it? Okay. So we're going to substitute in values into this equation, remembering that we can, if you want to do it, you can put in b into the 0 and it'll always be 1, doesn't matter. And then we'll get rearranging, find k. All right. So subbed in the values, there they are. So remember, that was the rate. So that guy there was 4 times 10 to the minus 5 moles per liter per second. That's what we've got to find. That was 0.1 and that was 0.1. Okay. So rearrange. K is rate over concentration of A squared. 4 times 10 to the minus 5 moles per liter per second over 0.1 m squared. Be careful with units, right? Okay, careful with units. That's going to cancel because that's to the minus 1 underneath now. When you bring it up, minus 1, right? Okay. So 4 point, just divide. 4.0 times 10 to the minus 3, 0.1 squared there. Careful, right? I just did that in my head. I'm thinking, oh, 5 and 3, that's not right by 0.1, but it's 0.1 squared underneath, right? So 4 times 10 to the minus 5 divided by 0.1 squared. One of the m's, it's going to be m squared as a unit underneath, one of the m's will cancel, it'll be m minus 1 second. Okay. So the units of K depend on the overall order of reaction, it turns out. There's a little cheat sheet in the back of the packet, you can look at it, but honestly, it's better to derive the units on the fly, right? So do this math every time, leave the units in, and they'll cancel, right, to give you what you want. Okay. So as I mentioned, the units of K depend on those of other variables. Actually, they depend on the overall order of reaction. And, be sure to quote the number and the units. Okay. So now we have a value of K, yeah? So if we go back to our question, right? So all the way back when, let's just double check what we got. We've got the rate law equation with numbers now, right? Because we have a number for K now in the unit. So we can use that rate law equation. We can use the quantitative version and find, hey, when A is 0.05 and B is 0.1, what's the speed? Okay. So there's our generic form. We're going to turn it into the quantitative form. K is 4.0 times 10 to the minus 3 moles per liter, minus 1 seconds, minus 1, A squared. If you like, B0 on the back, right? But again, B0 is 1, right? Okay. And just stick it in. So what I want you to do, okay, throw these numbers, actually this number in here, work it through, see what you get. Okay. All right. You back? Maybe you noticed the answer's at the bottom. Okay. So let's just go through it. Rate equals 4.0 times 10 to the minus 3 moles per. I actually prefer that, right? Per second is, oh, sorry. Throw the numbers in, yeah. The rate is 4 times 10 to the minus 3 moles per liter per second, a squared. This, I like to use seconds to the minus 1 instead of divide by seconds. And then, hey, remember that one? 0.05 squared, okay? So if you like that M goes, one of those M's goes, leaves an M. Guess what? The rate must always be, at the end of the day, moles per liter per second, right? Because we're working out rate 1.0 times 10 to the minus 5 moles per liter per second. Okay. Oh. There you go. Same as there. Okay. All right. Okay. So you saw me do one. Now it's time for you to do one. Okay. Now, honestly, when we have a test, this is very similar to what you'll get on a test. Okay. There's only so many ways we can ask the question. We can have more reactants and more products. So when we do that, in this case, we have 3 reactants. So we're going to have the baseline, and then we vary the 3 reactants systematically. We double them, right? So this is a standard kind of test, all right? Now, let's let you guys go at it, right? And then I'll go through it. Okay, so what I want you to do is determine the quantitative rate law expression, okay? So you need number and units for K, as well as the orders for each reactant. Okay, now here you've got 1, 2, 3 reactants, yeah? So M, N, just like we had before, and then we don't use O, alphabetical, we should, but we don't, because O is a bit like 0, right? So it's actually P, so M, N, and P, yeah? If we'd had a catalyst here, so maybe we had, some dissolved thing, maybe sodium or some hydro, I don't know, something, right? That would be a pseudo-reactant, and we'd actually include the catalyst, whatever its formula was, as a reactant. Okay, we'll see a couple of those down the road, maybe on the homework. But this one, non-catalyzed, so we don't need it. All right, now, so hopefully you tried it. If you haven't tried it, stop me and come back, right? But now let's go through it. Okay, so you could probably, let's just do one pair of data sets with the math, and then just do the rest with the observation, because it's actually easy to see it, isn't it, in the numbers. Okay, if we just look at that first real quick. So here's our baseline, 0.01, 0.01, 0.0005, right? Okay, obviously in experiment 2, this one's doubled systematically, then this one, okay? Look what happens when we double dihydrogen dioxide, hydrogen peroxide, right? So we double this one, the rate doubles, right? So times 2. So it's directly proportional. So that tells me, hey, if I double this and this one doubles as well, it's directly proportional. So that's going to be first order. We'll show you in a second with the math, but that's going to be first order through observation. Similarly here, compared to baseline, we double iodide, and it also goes up by a factor of 2, times 2. So that's going to be first order as well. I'm talking a lot about the first order. I'm a nerd. All right. And then finally, we look here, the rate does not change for H+, right? So that's going to be, if you like, times 1. That's going to be 0 order. So that's the trick, right? If you see a doubling, it's first order when concentration with respect to once doubled. If it doesn't change at all, it's 0 order, and if it's 4 times more, if you've doubled, it's second order, like we saw last time. Okay, but let's do the first 2 data sets. So remember, we've got this equation, right? All I'm going to do is take the second and the first, and then just divide them out, right? So for number 2, the rate is 2.30 times 10 to the minus 6. I'm a bit loose with units because they're all going to cancel. Equals K H2O2 to the M, I minus to the N, H plus to the O. Number 1, 1.15 times 10 to the minus 6 equals K H2O2. Oh, I should put the numbers in, shouldn't I? See what I did there. So number 2, I'll put them in. 0.02, 0.01, 0.0005. Here, I'm looking at 1, 0.01, 0.01, 0.0005, M and P. Okay, divide them out. Oh, apologies. I keep doing that. Okay, so I'm using this generic form but putting the numbers in, right? So for line 2, the rate's 2.3 times 10 to the minus 6 moles per liter per second equals K times the concentrations to their powers, right? 0.02, 0.01, 0.005. Line 1, baseline, same thing but 0.01 here. Divide it all out, I get 2, divide that, I get 2, equals K, just cancels to give 1, doesn't it? I'm going to write it. 2 to the M, and then 1 and 1. So therefore, M equals, hey, 2 equals 2 to the what? 1, right? Like we said. So we said here, because it was doubled, it's proportional, right? M equals 1. That's what we got. Okay. So therefore, we can look at the others. If I look at now, I just do some kind of example work, right? So here, when I look at 3 and 1, I'm looking at I minus, right? So for I minus, what have I got, right? I've got doubling. And it's kind of written backwards because it's the concentration to the power, right? And it went up by 2 again. Therefore, N equals 1 also. Fantastic, right? Then last one, see if we can do the last one. Hopefully you got this one too, all right? And when I do H plus, and this is kind of weird, if you have any kind of experimental experience, this is kind of making you go crazy because usually H plus makes things go faster. In this case, what happens? It's kind of interesting. So compare here and here. So again, I've doubled. What happened to the rate? It's the same, all right? So it's got to be 0. There we go, all right. So if I'm kind of keeping track of what I'm doing here, the rate equals K H2O2 to the 1, I minus to the 1, and H plus to the 0 so far, doesn't it? I'll do that bigger in a moment. Okay. Now, at the bottom, okay, all we're going to do, find the numerical value of K with units. So I'm going to take this equation and rearrange it. So K equals rate over, now we know what the orders are now, right? H2O2 to the 1, I minus to the 1, and I don't have to write H plus because it's to the 0 power, isn't it? Right? Okay, all I got to do, stick in some numbers. You can use any of these lines. I'm going to use the first line. Okay, so I'll use the first line. What have I got? 1.15 times 10 to the minus 6 moles per liter per second. Now, it's important to put units in when you do K, right? Over 0.01 moles per liter. Oh. And 0.01 moles per liter. Now, if you like, that one and that one cancel. That's going to come up and be the negative power equals, what have I got here? Oh, I guess I'm going to have to do it, aren't I? And we're back. And the answer is 0.0115. Units are moles per liter per second. There we go. Okay, remember M is moles per liter, right? Okay. All right. Hopefully that makes sense. Now, before we go any further, all right, I just flip over. The next thing we're going to do, if you think about it, this kind of makes sense, yeah, because when I first started talking about rates, I said, hey, we're finding essentially dy dx in a kind of a gross sense, right? So we do rise over run, change in one over change in the other is slope, yeah? That's essentially what calculus is, but dy dx is for a minute difference between two very, very close points. That's what dy dx actually means in calculus, isn't it, right? So if you think about it, we can use calculus, we can use dy dx math, if you like, to solve these problems, and that's called the integrated rate law expressions, okay? So it derives some equations in a moment which allows us to do calculus type things with these slopes, right? So if we know the equation of that line, and we do, okay, we see those in a moment, we can actually use calculus in a very similar way. It's not really an experimental method, it's kind of a, you have to have the equation of the line to do it, but you can use calculus. Okay, we'll get back to that in a little bit. But before we do, at the back of the packet, you got some good old exam questions, right? Now, here's something pretty interesting. As you know from Chemistry 101, when you take the ACS final, the ACS has an interesting way of asking you questions, doesn't it? Right? And once you get used to the pardon me. That's better. Once you get used to the ACS style, it's not actually that bad, right? So let's look at this equation, right? Let's look at this question right here. So this is a typical ACS style question. Right? Let's take a look at it. So for the reaction A plus B goes to C, popular reaction. Okay. Obviously, rate equation has the form rate equals K A to the X, right? Now here's the interesting thing, therefore, it's a bit like that one we looked at earlier. B is zero order, isn't it? Because it's not appearing in the rate equation. Okay, so what is the value of X? In other words, what's the order if, right, the rate triples, now remember, concentration to the order equals rate multiplier. All right, so if we think about that, right, watch this. So the rate triples, so the rate went up by 3, right, I'll just kind of keep that there, right. When A triples, so that went up by 3, right, so what's X? Got to be 1. So that's one of those observational ones, but it's not doubling, it's tripling, right? So if you see a tripling of rate for a tripling of concentration, it's first order, right? If it went up by 9, it'd be second order, because 3 squared is 9, right? Okay, I think I might have told you something. Okay, the rate increases 8-fold, so 8, that's the rate, okay, rate again, right, equals, this is doubled, right? So this is doubled, so 2 squared is 4, 2 cubed is 8. Very rarely you'll get a third order. For reasons we'll talk about later, it's going to be third order, right? That's the third order, right? First order, third order. No brainer. Last one. There is no change in rate when it's tripled. No change in rate. So rate was 0. This guy was tripled, right? X equals 0. Okay. 0 order. If you don't see a change in rate, it's always 0 order. If you see a proportional, it's first order. If you see a squaring, it's second order. All right. What trick was being tested? Well, it was this, I'll actually write it around, actually, it's concentration to the order equals rate multiplier. That's what's being tested. Okay. Now, hopefully you're feeling confident, right? Hopefully you're feeling confident We've done a couple now, yeah, we've done a couple now. I'm going to set this one for extra credit homework, and as you now know, extra credit's due on Wednesday, okay, or before Thursday, right? So try this one. If you get it to me before Thursday, give you 2 points extra credit. You know, it's probably your best idea just to kind of print this if you can, and then just write on here, and then just take a quick picture. Now, I'm not as strict with, you know, extra credit, right? On a test, and several people are still confused on this, on a test, you've got to follow the rules, right? And it's kind of more formal. But here, just a couple of points of extra credit, you can just take a picture, okay? So, the usual thing, find the order with respect to each reactant and then get the qualitative version of the rate equation, okay? Put the powers in. It says to do it right there. Find the value of K and its units. And then, you know, when they're both, when they're all 0.5, what's the speed? Okay, so it's quite similar to one we did before. All right. Okay. I'm going to stop there. I'll bring you part 2 with the integrated rate law shortly. See you in a minute. Okay, we're back. Now, integrated rate law. So, just a little bit of a recap, then we'll get into the math. Okay, now, if you wondered why you had to take like math, was it 138 to get into this class as a prereq? It's because there is a limited amount of, if you like, higher end algebra and a little bit of calculus, all right? So, meet that in a minute. Okay, now we're going to derive some things. You wouldn't be asked to do that on a test. We're just going to show you where it came from. And you've got to have kind of an understanding of that kind of theory. Okay, so let's take a look. So, quick recap first. Okay, remember our classic graph here. Okay, so the initial rate is the slope at t equals 0 of the concentration versus time graph. Okay, an average is just the gross amount of concentration lost over the entire time. As you can see, the initial rate is much steeper than the average because it's faster at the beginning. This is just an average over all time. It's kind of similar about halfway through, which makes kind of sense, and then it's flat right at the end. At the end of an experiment, rate 0, that's how we know we finished, rate 0. Okay. Finding the tangent at any point on the line, rise over run, gradient is speed of reaction. Moles per liter per second usually is the units. All right. We can find that gradient by tangent or by adjacent points. So we talked about the 2 adjacent points method. Several of you sent me some extra credit on that. Thank you for that. All right, good job. Or you can, you know, have the computer tell you what the tangent line is, the gradient and the tangent, sometimes. All right. Now, we then looked at the data from an initial rates experiment. So we take a bunch of initial rate data, the slope at time equals 0, for a bunch of experiments where we systematically change the concentration of the reactants. So we have a baseline, we double one, we double the other, and if there's a third, we double that one. And then we just do the mathematical treatment or the observational method to get the rate equation, okay? We can find values for K with units and the powers, okay? And that's where we are, right? Now, when we get onto this new stuff, let's just consider a very, very basic example. And it'll give us the equation we want, right? Okay. So here's a very, very simple reaction. A turns into B, okay? So it's just collisions involving A. The question is going to be, is it first or second order, okay? So for such a reaction, just, you know, does A fall apart by itself? Or does it bump into another A and they then fall apart? I don't know, there's some mechanism we don't know, right? But it's either going to be first order, and we'll get something like that, first order, or it's going to be second order, right? Okay, because there's only one reactant, it can't be 0, can it? Okay, now, assuming K was similar in each case, right, which would be the faster process and why? What do you think? What's quicker, a first order or a second order process? Obviously second order, right? Because it's that exponential term on rate. So let me just rephrase that. So the rate is kind of dependent exponentially on concentration. So the concentration we saw doubled, the rate might go up by a factor of 4 because it's squared, right? Okay. So obviously second order is faster because we got A squared is proportional to rate. Okay. So I double the concentration, square that, the rate's 4 times faster. Okay. All right. Why not do first order as well, slower, because a to the 1 is proportional to the rate. So if I double the concentration, I double the rate, not quadruple it, because it's proportional. Okay, so if I then looked at my standard lab plot, right, what would I see? So if I had a first order equation, this is concentration and time, right, in each case. This is concentration. So if I had a first order plot, it's going to be kind of shallow like that, right? It's going to have the classic shape, but it's going to be shallower. It means it's slower because the gradient's going to be shallower, right? But if I had a second overall, it might be sharper like that, right? So that's shallow, which is slow, and this is steep, if you like, which is fast. Okay, so that's generically what first and second order plots look like. I've exaggerated the shapes, okay? If you were to plot these in lab and just look at the shape of the graph, you could never tell, particularly because like lab software likes to kind of fill the page. You can't tell, all right? So unfortunately, you can't tell by looking. You've got to do the math, okay? But would you be able to look, with all other things being equal, the slower one would be shallower, the faster one would be steeper, right? Because if you look at like some point in time here, maybe, right? Oh, that's a bad point in time. Here's a good point in time. So the gradient there is steeper than the gradient there, isn't it? It's faster. Okay. All right. So first order processes have shallower curves. Second order processes have steeper curves. Now, remember, we want to somehow mathematically manipulate this issue, right? So we want to kind of take the equation of that line and then do some math on it, right? So what math equations kind of look like that? Exponential decay like that? Well, 1 over x and 1 over x squared. That's going to be the steep one. That's going to be the shallow one, right? Okay. So that's first order, that's second order. You can use other functions. I've written it down here. This is kind of older. So the functions we like to use for this kind of entry-level stuff is 1 over x is the function we'll use for first order. 1 over x squared, steeper, is for second order. Okay. So those are the equations of the line, and if you like, y equals. It's going to be concentration equals, yeah, okay. All right. So there we go. Now, humans, right, we, humans, don't like exponential line shapes, yeah? We hate this kind of math, don't we? We like to have y equals mx plus b, a nice straight line. Okay, so the question is, and this is why we do this integration, how do we turn these functions into linear functions? Well, we use some calculus, right? So, make sure I get this right. I'm a bit rusty on calculus, but we'll do it. So how can we take these non-linear shapes and turn them into linear lines, right? Linear lines? Linear graphs. Okay. So, so rate, remember rate equals this, right? Rate is change in concentration over change in time. That's rate. Rate equals, for the first order, Ka to the first power, right? Okay, now let's do some derivation. Right, so if I like, the integration, if I take this over, so you know, what's it, integration by parts, right? So I'm going to take things common to both sides, right? So I'm going to take t over here and a over here. So I keep the a's together, take the t over there, right? So I'll put a minus in front, minus let me get this right. So I'll bring this one over, delta. So instead of writing big delta, I'm going to write small delta like we do in calculus. Okay, so see what I did there? I took this over here, this over here. This is the integral variable, right? Equals the integral of kt. So the integral of 1 over concentration with respect to concentration equals the integral of k with respect to t. Nope, delta t. Delta t. There we go. All right. Fair enough. Now, let's do some like tricks, right? So that I'm going to multiply through both sides by -1, And k is a constant, right? So therefore, the integral of 1 over a dA equals the integral of k minus k times 1 dt. All right. Remember the limits, right? So the limits of concentration were A0, which is the concentration at time 0, and then just the concentration at time t, right? So concentration at time 0, concentration at time t, and then concentrate time 0 and time t. Those are my limits, right? So here, now, what's the integral of 1 over x? All right, let's do this on the side. The integral of 1 over x equals ln x, natural log, right? Natural log. So, if I just integrate this, natural log of a at time t minus natural log of a at time 0 equals minus k times 0, which is 0, and then kt. Oh, kt. There we go. All right. Interesting, right? So, flip that over. So there's the equation I just had. I'm just going to rearrange that, right? So then I've got y equals mx plus b. There we go. Okay. So that is your straight line version integrated rate law equation for first order, right? Okay. Now let's before I expose this bottom part, right? Think about what that's going to look like when we plot it. Yeah. Okay. Y variable is natural log of concentration, right? Along here, x is t. Okay. It's going to have a negative slope, and a negative slope is going to be k, right? And the intercept is, makes sense, the concentration at time 0. It makes sense that the concentration at time 0 is high because it's a reactant. It's going to be high at the beginning. And there it is. Okay, so there's our linear first order plot. So if you've got some experimental data, right, if you plotted, and this is, if we do this in the lab, it's fantastic because with our machines, we can just click on the left axis on the screen and change it from just concentration to natural log of concentration, and it goes linear. If it goes linear, when you plot natural log concentration versus time, if it goes linear, it's a first order process. And this is what you do to actually interrogate data, right? So you'd actually look at the data. You can't tell by, as we mentioned, you can't tell by looking at these graphs, right? But then when you plot them, natural log of concentration versus time that goes straight, the slope's k, and it's first order, because the first order will be linear when natural log is plotted. Okay. If we look in the back of the packet, and it talks about it down here. All right. So I can find that for you. Oh, actually it's over there. I've got my appendix sitting over here. Not the appendix. So, yeah, here it is. So, if I look at some actual data, right, so that's the natural log of whatever that is, SO2CL2 versus time from an experiment. It's linear with that equation. Okay, all right. So I'll put that to one side. It's in the appendix, take a look. Okay, so that's a reactant decomposes to form these products. Reactant decomposes to form these products. If I plot natural log of concentration versus time, our classic exponential decay turns into ln concentration time, straight line, linear, and you do a regression line, 0.99 or whatever would be the fit, be straight. Okay. All right, that's first order. So associate natural logs with first order, right? Now, we'll do the same thing for a second order. Okay, so we'll do our integration again. This one, hold tight, right? It's a little bit more involved. Right, so again, rate is this, right, which equals Ka to the second power for a second order process, right? So therefore, because it's going away, minus the integral of, and we'll do the same thing, right, bring A over, a T over, all right, so it's 1 over A squared dA equals, same as before, right, Kt. Put the units in, sorry, the limits of integration. Okay. Now, I'm going to leave the minus over there for a reason you'll see in a minute, because do you remember what your integral of 1 over x squared is? Minus 1 over x, right? So hey, if I keep the minus over here, minus times a minus is a plus. Okay. So, okay, if you like, minus times a minus is a plus, right? Oh, 1 over, so I just cross that out, 1 over a t minus 1 over a 0, which equals kt. So same as before, right? Okay. Rearrange that. What do I get? I get this. So that's the variable, that's the constant, k and t like before, right? So if I rearrange that, I get y m x plus b. So if I plot that, right, I'm going to have 1 over concentration up the side, time along the bottom, right? It's going to be positive slope with an intercept, right? So that's going to be 1 over a0, and that's going to be k again. So the slope's always k, but it's going to be a positive slope, not a negative slope. So again, if you plot the reciprocal, and again, if you're in lab, you just press the side axis and change it to 1 over concentration, right? If you get a straight line, positive slope, nice straight line, it's second order. So that's what you do in lab. You can just kind of plot these things very quickly on a calculator or a computer to get linear plots. Whichever's the most linear is the one that's the correct order. Okay, and there it is. So there's your intercept, there's your variable, there's your time. If we look at this, so say we did this experiment in lab, we looked at NO2 falling apart to make NO and O2. We got our, traditional plot. We can't tell by looking, right, of concentration versus time. We can't tell by looking if it's first or second order. We can't make the determination by eye. We have to plot natural log versus concentration, natural log of concentration versus time, reciprocal concentration versus time, whichever is linear is correct. We see here we get a bad fit, discard. We get a good fit, accept, and we get a nice equation for the line there. And 0.255 would be k, right? Whatever the units are for second order. Okay. Worked example. So I've got the answer. Okay, now on the test, this is the one that always trips people up for whatever reason. Okay, it always trips people up. Okay, and I think the reason it trips people up is because they don't recognize it's the integrated rate law question. Okay, despite lots of hints on the test, which you'll see when you look at an old example, right? Okay, so first you've got to recognize it's an integrated rate law example. Let's talk about how we do that, and then we'll solve it, right? So let's see what they've given us. This reaction, N2O5, turns into these products, right? They've already told us what the order is. So it's not an initial rates question because we've already got the quantitative version of the rate law equation, right? Okay, so we already have K, and we already have the order. So it's not initial rates, it can't be, right? Okay, so what can it be? It's got to be integrated rate law, right? So they've given us this information, that's key, right? If you look at the information they give you, that should be a clue. They've given you the order, they've given you K. So because they've given you order, you know it's going to be the natural log one to use, right? Because it's first order. All right. So if the initial concentration, they give us A0 as well, right? Initial concentration and a time, we can figure out using our equation. The initial concentration is this. What's the concentration after 625? Okay. So the plan. Now I'm going to let you guys have a shot at this, right? I'll give you the plan now. write down what is given. What did they give us? Well, I'll do it generically. A0 equals 5.0 times 10 to the minus 3 moles per liter. T equals 625 seconds. And also K equals 4.8 times 10 to the minus 4 second minus 1. And it's first order. So now we've kind of identified the goodies, right? We can use integrated rate law for first order. Solve for concentration at 625. Okay, give it a shot. There's some tricky math in there involving inverse functions. If you remember, the inverse function of a natural log is e to the x. There's a hint for you. Okay, so pause me, give it a shot. All right, you're back. So what we got? Natural log of a, let me get this right, t equals minus kt plus natural log of a, 0. Okay, so that's our equation, right? Okay, we're just going to plug in the numbers, right? So I'll just write it underneath. K, 4.8 times 10 to the minus 4 seconds to the minus 1. Careful with the units, right? Because seconds to the minus 1 times seconds, it just gives me a number, right? All right, which we'll need in a minute. So then, 625 seconds, right? Plus natural log of 5.0 times 10 to the minus 3. Now, when we start doing logs and exponents, units disappear, right? So you've probably seen that in math, right? So what we get, so this equals 0.3, oh, minus 0.3, and we're going to, natural log of a small number is a minus number, so it's going to be minus, if you like add a minus number is minus a number, 5.29, which equals minus 5.59. So therefore, natural log of a t is minus 5.59. Interesting. Now here's the thing. How do we get the concentration at 625, right? Well, look on your calculator. All right, so if I find my natural log button on my calculator, if I can find the darn thing. Okay, there it is. So there's the natural log, and the inverse function is e to the x, yeah? So all buttons on calculators are toggle, right? So you go the other way. So second function would be e to the x, regular function, natural log. All right, so plus minus are inverse functions, right? Multiply, divide are inverse functions, yeah? Log and exponents are inverse functions, right? Natural log and e are just base e, right? So if I do the inverse function to both sides, it still stays equal. That's the big trick, right? So I'm going to go e to the natural log ea equals e to the minus 5.59. That, oh, there we go. E to this equals e to this. That just disappears. So a equals e to the minus 5.59, which equals that number. 3.7 times 10 to the minus 3. All right. Okay, now that was the weird one, right? Okay. To get rid of a natural log, you take the answer, so you work out what that is, right? And you raise e to that number. Okay. All right. And there it is. Okay. Okay. Next one, a very kind of interesting application of the integrated rate law is what you've probably seen somewhere before, maybe in geology, perhaps physics, perhaps in a chemistry course before, which is half-life. Okay, now I'm not talking about the video game, or some people do say have a striking resemblance to Gordon Freeman. I'm not talking about that. I'm talking about half-lives in terms of reactions. Now, you've heard it in terms of radioactive decay, right? So I have a nucleus of uranium, right? And it has a half-life of 5,000 years or something, right? So that means, what does it mean? It means that uranium half of it will go away in 5,000 years. It's the time taken for half of it to react, right? be it a nucleus falling apart or just a molecule doing something, right? So reactions also have half-lives, because half-life is very simply defined as how long it takes to get half as much stuff you started with, right? So half-life, simple phrase, how long it takes to lose half your stuff. We have a joke in our house. It's that chocolate has a very short half-life because half the chocolate's gone after 10 minutes. Chocolate has a half-life of 10 minutes. All right. Now, if we talk about that in more kind of realistic kind of chemistry terms, all right, so T1/2 equals time taken for concentration of reactant to decrease by half. All right. So how long it takes for half of it to go away. All right. So if I'm thinking about it in just terms of fractions, if I start with 1 mole per liter, say, right, after 1 half-life, and we write T1/2, I got 0.5 moles left, right? And then the clock starts again, because now, you know, I've gone from 1 to a half, right? That's half of 1, right? And then after another half-life, well, I'm starting at 0.5 now at this point in time. And after another half-life, I've got 0.25. After another half-life, I've got 0.125, an eighth, right? So that's a half, that's a quarter, that's an eighth. And that's your classic fractions, right? So as after 1 half-life, you've got half as what you originally had. After 2 half-lives, half of a half is a quarter of what you originally had. After 3 half-lives, a half of a half of a half is an eighth, right? Okay. All right, so we see that nicely down here. If you count up all the little dots, there's 24. After 1 half-life, I got 12. After another half-life, I got 6. After another half-life, I got 3. Okay? So that's a first order, this is first order decay, right? So half-lives for first order. Now, for the math of that, you can actually take that integrated rate law expression and you can actually sub in some very simple numbers and come up with an equation, right? Okay, so if you think about it, here's the trick. By definition, after 1 half-life, I've got half as much stuff, right? So so at the beginning, right, so let's say at the start, we've got 2 moles per liter, right? So after 1 half-life, so A at 1 half-life equals 1, right? So after a half-life, half of 2 is 1. If I do that, it makes the math easy, right? Okay. Now, let's just stick it in the equation then. So natural log of the concentration at the half-life equals minus K, the T is the half-life, plus natural log of A0. Okay. Therefore, natural log of 1 equals minus KT for the half-life plus natural log of 2. Now, you may remember this lovely log math, right? Okay. Do you remember this one? Natural log of x plus natural log of y equals log of xy, and natural log of x minus log of y equals natural log of x over y. Remember that? Yeah. All right. So if I go here now, so if I just rearrange this, yeah, I want to get this positive, right? So k t to the half equals, all right, bring that over there, bring this over here, ln2 minus ln1, which equals ln2 over 1, which equals ln2. So if I just rearrange that one more time, therefore, make the half-life the subject, T1/2 equals ln2 over k. And you can rearrange that to find k as well. All right. So that's actually in the, that'll be in a data sheet. I've got it, a data sheet at the back here. All right, so that's my first order. The natural log of 2 is 0.693. Okay. All right. Now, you can do a similar thing with the other equation. all right, you will get t a half equals, for a second order, right, 1 over k a0, right? Extra credit plus 1. Just do that derivation for me. You don't have to know how to do that derivation. You only need the equations, right? And they'll be on a data sheet. But if you can do that similar kind of math, but for a second order, I'd be impressed to give you a point. All right. I'm about to run out of time, so I'll stop briefly and come back. Okay, so the last page when we do that little bit extra credit, there's like a data, a little cheat sheet. Just the stuff we talked about. So 0, first and second order. We have the units of k, which I suggest you work out on the fly rather than memorizing. Then we've got the integrated rate law. We didn't do a 0 order one, but there's our first and second. There's the graphs, linear slopes, and there's our answers for the half-life when we sub in 2s and 1s. Okay, now, what we got here is a deceptively simple question. Deceptively simple question. So we have, for the reaction, this thing falls apart to make products. It's first order, all right? So we're going to use the standard t a half equals 0.693 over k, right? Okay. So assuming this is first order, what's the half-life? That's easy, right? You just solve it, yeah? So I'll give you a couple of minutes. Try solve that, and then it goes back. And this is where you get those magic fractions, right? Remember this? So if you see half, quarter, or an eighth, or if you like, 0.75 gone is the same as 0.25 remaining. Trick, right? If you've got these magic fractions, it's just a multiple of the number of half-lives, right? It's not a linear function, right? So unless it's exactly a half, a quarter, or an eighth, you can't use the fixed number of half-lives, right? You've got to actually solve it, right? But that's what's happening down here. Okay, give you a minute, try it. Okay, you're back. All right, so the half-life, nice and easy, right? T a half equals 0.693, which is ln2, over 2.2 times 10 to the minus 5, seconds to the minus 1, seconds minus 1. Yep, you have to excuse that phone there. I'm going to pause while that finishes its business. All right, sorry about that. Okay, so we're back. So how long would it take for 50% of it to decompose? So that's 1 half-life, right? So that's 1 times t a half, which equals 3.15 times 10 to the 4 seconds. 8.75 hours, right? Okay. How long would it take for 75%? So that means 25% left, right? So that's, you get after 2 half-lives. So that's 2 times t a half. 2 times 3.15 times 10 to the 4 seconds equals, well, in regular money, that's 17 and a half hours. It's interesting, you can quote it in seconds, but like if there's a nicer kind of integer to use, so that would be 8.75 hours, and that would be 17.5 hours, twice that. Okay. All right. Now, I think we're left with one more problem here, okay? And I'll go through this with you, okay? Well, actually, I want you to do it, right? So I'll give you the answer, but I'll talk you through the steps, right? So we have this decomposition, first order, right? Okay, so same equation as before, okay? And here's an interesting thing. So the concentration of N2O5 may be monitored using a simple diode calorimeter, right? So colorimeter, rather. So the absorption of the color is proportional to concentration. Whenever you see that, understand Beer's law. So absorption, how much light's absorbed by colored material, is proportional to how many things are in the way. That's the concentration, right? So we're just going to use absorption instead of concentration, and it works just the same, okay? So try that one out, right? There's your K. Concentration, what's the half-life? Work it out, right? There's K, all right? Just like before, 22.2 minutes, right? Now, if in the above experiment, The absorption was 0.84, so if you like A0 equals 0.84, right? What would the absorption value be after one half-life? After one half-life, what happens? Half as much, right? So what's half of 0.84? 0.42. Now absorption is just a fraction, so no units. Okay. In the above reaction, what absorption were recorded by the colorimeter after 3 half-lives? 3 half-lives means half, quarter, eighth, right? So it's going to be 0.125 times 0.84, which equals 0.105. Hopefully that's easy. Okay, it's a nice easy one to finish. Okay, stop there. I'll get this posted. Again, any questions, office hour, or we'll call the chat, or discussion. All right, see you next time. I love this part.